In this episode of Exploring Data Science, we'll consider the concepts of generalization, fitting and overfitting, cross-validation, learning curves, and complexity control. For more in-depth reading around these topics, you can refer to Chapter 5 of the book Data Science for Business by Provost and Fawcett. One of the most important fundamental notions of data science is that of overfitting and generalization. If we search hard enough for patterns in a particular dataset, we will find patterns. Unfortunately, these patterns may be just chance occurrences in the data. We are interested in patterns that generalize, that predict well for instances that we have not yet observed. Finding chance occurrences in data that look like interesting patterns but which do not generalize is called overfitting the data. Let's consider an extreme example. We're given a large data set of customers and asked to produce a model to distinguish customers who are likely to churn or leave based on some features. We build a model that is 100% accurate. It does not make a single mistake, identifying correctly all the churners as well as the non-churners, but only on the training data. In fact, what we actually did was store the feature vector for each customer who is churned in a database table. If we pass a feature vector from the training set into the so-called model we have created, it will always return the correct result. This is essentially called a table model and is mostly useless when used with any real data beyond the training set, unless you happen to have a customer with a feature vector that exactly matched that of another customer in the training set. In reality, no one would throw raw customer data into a table and claim it was a predictive model of anything. But it's important to think about why this is a bad idea, because it fails for the same reason other, more realistic data mining efforts may fail. It is an extreme example of two related fundamental concepts of data science: generalization and overfitting. Generalization is the property of a model or modeling process whereby the model applies to data that were not used to build the model. In this example, the model does not generalize at all beyond the data that were used to build it. It is tailored or fit perfectly to the training data. In fact, it is overfit. We want models to apply not just to the exact training set, but to the general population from which the training data came. All data mining procedures have the tendency to overfit to some extent, some more than others. The idea is that if we look hard enough, we will find patterns in a dataset. As the Nobel laureate Ronald Coase said, if you torture the data long enough, it will confess. The answer is not to use a data mining procedure that doesn't overfit, because all of them do. Nor is the answer to simply use models that produce less overfitting, because there is a fundamental trade-off between model complexity and the possibility of overfitting. The best strategy is to recognize overfitting and to manage complexity in a principled way. To examine overfitting, we need to introduce a concept that is fundamental to evaluation in data science: holdout data. Evaluation on training data provides no assessment of how well the model generalizes to unseen data. What we need to do is to hold out some data for which we know the value of the target variable, but which will not be used to build the model. Creating holdout data is like creating a lab test of generalization performance. We will hide from the model, and possibly the modelers, the actual values for the target on the holdout data. A fitting graph shows the accuracy of a model as a function of complexity. Here we have a typical fitting graph. Each point on a curve represents an accuracy estimation of a model with a specified complexity, as indicated on the horizontal axis. Accuracy estimates on training data and testing data vary differently based on how complex we allow a model to be. When the model is not allowed to be complex enough, it is not very accurate. As the models get too complex, they look very accurate on the training data, but in fact are overfitting. The training accuracy diverges from the holdout or generalization accuracy. In short, there will be more overfitting as we allow the model to be more complex. Here we have a typical fitting graph for tree induction. Beginning at the left, the tree is very small and has poor performance. As it's allowed more and more nodes, it improves rapidly, and both training set accuracy and holdout set accuracy improve. Also, we see that training set accuracy always is at least a little better than holdout set accuracy, since we did not get to look at the training data when building the model. But at some point, the tree starts to overfit. It acquires details of the training set that are not characteristic of the population in general, as represented by the holdout set. In this example, overfitting starts to happen at around x equals 100 nodes, denoting the sweet spot in the graph. In order to have a fair evaluation of the generalization performance of a model, we should estimate its accuracy on holdout data. That's data not used in building the model, but for which we do know the actual value of the target variable. While a holdout set will give us an estimate of generalization performance, it is just a single estimate. Is this single estimate enough for us to have confidence in the model? Well, this is where cross-validation comes in useful. Cross-validation is a more sophisticated holdout training and testing procedure. Cross-validation makes better use of a limited data set. Instead of just splitting the data into one training set and one holdout set, cross-validation computes its estimates over all the data by performing multiple splits and systematically swapping out the samples for testing. Cross-validation begins by splitting a labeled dataset into K partitions, called folds. Typically, K will be 5 or 10, for example. Cross-validation then iterates training and testing K times in a particular way. As depicted in the image shown, in each iteration of the cross-validation, a different fold is chosen as the test data. This example shows 5-fold cross-validation. The original dataset is split randomly into 5 equal-sized pieces. Then, each piece is used in turn as the test set, with the other 4 used to train a model. The result is 5 different accuracy results, which then can be used to compute the average accuracy and its variance. We can use this cross-validation technique to not only understand the performance of a single model, but we can compare the accuracy between different model types. For example, if we've developed one model using logistic regression and one model using classification trees, we'll be able to identify which model type performs better on the test data. The images here show the fold accuracies for cross-validation on a classification tree model on the left and a logistic regression model on the right. We can see the accuracy of the models varies across each fold, and this is expected. The horizontal line on each graph shows the average accuracy of the folds. We can see that the logistic regression model approach shows slightly lower average accuracy, around 64%. There is also a higher variation, or in fact a standard deviation of 1.3, compared to the classification tree approach. On this particular dataset, classification trees may be preferable to logistic regression because of their greater stability and performance. But this is not absolute. Other datasets will of course produce different results. To improve the generalization performance of data-driven modeling, we can test it against more training data. A plot of the generalization performance against the amount of training data is called a learning curve. The learning curve is another important analytical tool. A learning curve shows the generalization performance, the performance only on testing data plotted against the amount of training data used. Learning curves usually have a characteristic shape. They are steep initially as the modeling procedure finds the most apparent regularities in the dataset. Then, as the modeling procedure is allowed to train on larger and larger datasets, it finds more accurate models. However, the marginal advantage of having more data decreases, so the learning curve becomes less steep. In some cases, the curve flattens out completely because the procedure can no longer improve accuracy even with more training data. In the graph shown, the improvement rates are different for the two model induction techniques and change over time. Logistic regression has less flexibility, which allows it to overfit less with small data, but keeps it from modeling the full complexity of the data. Tree induction is much more flexible, leading it to overfit more with small data, but to model more complex regularities with larger training sets. The learning curve may also show when generalization performance has leveled off, so investing in more training data is probably not worthwhile. Alternatively, the learning curve might show generalization accuracy continuing to improve, so obtaining more training data could be a good investment. The main problem with tree induction is that it will keep growing the tree to fit the training data until it creates pure leaf nodes. This will likely result in large, overly complex trees that overfit the data. We have two options to help solve this problem. First, we could stop growing the tree before it gets too complex. Or second, we can grow the tree until it is too large, but then prune it back, reducing its size, and therefore its complexity. The simplest method to limit tree size is to specify a minimum number of instances that must be present in a leaf. This way, tree induction will automatically grow the tree branches that have a lot of data and cut short branches that have fewer data, thereby automatically adapting the model based on the data distribution. To review, why is overfitting bad? As a model gets more complex, it's allowed to pick up harmful, spurious correlations. These correlations are idiosyncrasies of the specific training set used and do not represent characteristics of the population in general. The harm occurs when these spurious correlations produce incorrect generalizations in the model. In summary, data mining involves a fundamental trade-off between model complexity and the possibility of overfitting. All model types can be overfit. There is no single choice or technique to eliminate overfitting. The best strategy is to recognize overfitting by testing with a holdout set. Several types of curves can help detect and measure overfitting. A fitting graph has two curves showing the model performance on the training and testing data as a function of model complexity. A fitting curve on testing data usually has an approximate U or inverted U shape, depending on whether error or accuracy is plotted. The accuracy starts off low when the model is simple, increases as complexity increases, flattens out, then starts to decrease again as overfitting sets in. A learning curve shows model performance on testing data plotted against the amount of training data used. Usually, model performance increases with the amount of data, but the rate of increase and the final performance can be quite different between models. Cross-validation is a systematic way of splitting up a single dataset so that it generates multiple performance measures. This then gives us the average behavior of the model as well as the expected variation.